Hello, welcome to another video where I'm going through the Rust programming language book, which is available for free online but also in print. So in today's episode we're going to be looking at ownership, some code examples that illustrate ownership and scope. I'm going to actually slow roll this, so section 4 of the book I'm going to actually break down into 3 videos because I really do need to get my head round ownership and all the implications in Rust, because I must admit I've not programmed a great deal in systems languages. I've done a little bit of programming in C and C++, but from my perspective it's obviously really important. So what I would suggest anybody watching this video does is, before they go any further, they actually stop the video and read through the section in the Rust programming language about ownership. So what is ownership 4.1? Because there's a really cool bit here that explains about the stack and the heap using a great couple of examples. Also, there's things that I could talk about in this video to do with memory and allocation, which I don't really want to struggle through. That sort of stuff would take me a lot of work to produce graphics to show all of this, and why bother when someone's taken the time to write a book out. So I'm purely going to stick to running some of the code examples, and I'll explain contextually why, what's going on. So we're going to be talking about ownership and scope in this episode, but I would highly encourage you to read through this section of the Rust programming language book if you're trying to learn Rust. If you're just using this video as a way to help you relax, then just watch the video and enjoy. Okay, so what exactly is ownership in Rust? And I've done my usual thing where I've got my code and I try and remember to highlight the code in amongst all of the comments. So these are just comments for me, so I can remember what the hell I'm talking about. So in Rust, ownership is a set of rules that governs how a program manages memory. In other languages, they might do that using always-on garbage collection. That's something I've certainly come across before, or by a programmer explicitly allocating and freeing the memory. I've also programmed one time, I'm trying to remember what language it was, where I had to periodically force a garbage collection to stop me running out of memory, where I had some quite complicated arrays going on. So periodically it would do a garbage collection on the memory. In Rust, how it's done is through a system of ownership with corresponding set of rules. So, and with Rust being a systems programming language, it's really wise to understand how the stack and the heap work. And as I mentioned at the start of the video, there's a very good description with a helpful analogy in the Rust programming language book in section 4. So I would definitely read that. Having a good understanding of the stack and the heap and memory allocation is a really good really good knowledge generally when you're working in programming. So definitely read that before doing any programming in Rust where you're going to be writing code that involves variable manipulation, which is probably from the get-go, particularly things like arrays and string manipulation. I've often seen other programming language courses where they sort of focus in on arrays and strings and characters to show where problems with memory allocation can go horribly wrong. So, but to highlight some of the key points of section 4.1, I'm going to be going through some code examples here basically, and I'm not going to talk about the ins and outs of the heap and the stack. Ownership, basic ownership rules in Rust. So each value in Rust has a variable that's called its owner. There can be only one owner at a time. There can be only one. So, yeah, very Highlander. When the owner goes out of scope, the value will be dropped. So you've got there so ownership is helping, ownership and scope is sort of helping keeping things nice and clean. But like I said, that section does a really good job of explaining how that works in relation to the heap and the stack. So definitely read through that. And in the first example, I'm just going to show you some basic concepts of scope if you're not familiar with scope at all, or haven't really fully explored it. So here's the code plus this bit here as well, which I'm going to uncomment in a moment. So we're going to do some very simple things here. We've just got this variable here, which we're defining. So here, talking about it in the sort of ownership language, what's actually happening here? Well, we have this variable SM, and it's being assigned ownership. It's the owner of this string literal hello. Then we've got a block of code. So I've created a block here. Again, this is using the example from the chapter, from the section in the chapter, and this block's been deliberately created to force scope. And within this block of code, we've got another declaration here, another thing going on where we're saying let SB equal hello. And here again, it's an ownership thing going on as well. So the variable SB is the owner of this particular hello literal. So as we move through the block, in terms of scope, so here we get into the block, but we haven't defined SB yet, so it's not valid, it's not been declared yet. If we tried to reference it, we'd get an error. However, SM, which was declared here, is in scope, and it still is as it was declared in an outer block. Here's where we declare SB, so it's valid from this point forward, and then we print it. We get to the end of the block and the scope's over, so SB is no longer valid. Additionally, I'm printing from main, from outside of the block, so the next line after the block, after the previous block is finished. I'm printing out SM just to prove what's going on here. And you can see over here, I've already run this code, so that's the bit. So we've got hello from main, but in the block. That's that line there. Hello, copy of SM as, hello from the block and in the block, which is this one here. This is SB being printed. And then finally, hello from main. So there's a print for SM again. And you can see SM works within main and within the block because it was declared in main. Now let's just see what happens if we uncomment this. So here we're going to try and attempt to print SB, which was defined in the block, and let's see what Rust says to us. Oh, it's not happy. A local variable with a similar name exists. So again, this is really cool. So basically, SB's out of scope. Well, we know that, but we deliberately did it. We deliberately broke it. not only is it telling us SB is out of scope, but also it's saying, well, you know, you've got this other variable that you've declared. It has a similar name. You sure you didn't mean to use that? Now, in this case, I didn't. I just mistakenly printed the SB outside of the block that it was defined in. Okay, so that's the first example. So let's just consider some more ownership and scope examples relating to various variable types. And again, in the book it goes into a lot more detail. Here I'm just skimming the surface program using some code examples. Okay, so here what we're going to do is we're going to just again take that previous variable and, you know, effectively, I suppose, copy it. So we have a string literal in the form of SM, and then we're just going to copy it to S2 and make S2 the same value. And in a lot of programming languages, this is where things can get a little bit weird. So with this, it will work fine. So you see, hello copy of SM as SM2 from the main. So I took that SM variable I'd previously declared and copied it to S2, and it's quite happy with that. So everything seems okay, and string literals are convenient, but they're not suitable in situations where we need to manipulate, so mutate them in some way, or they're unknown until some user input occurs, so we can run into problems before that. So in those examples, it's better to use a second string type, and this is the second string type available in Rust. And here we're using the from function to create a string from a string literal. So we're still doing it from a string literal, but our variable is now the second type of string. And you can see string from this. Again, the examples are pretty simple. You know, there could be a whole load of other ways this string came in. It could have been through user input. Now I've done this, so that's one thing I can do. I can just create this, and if I print this, you can see in the print I've actually just appended world on the end there. So I'm printing STS, and as part of the print ln macro, I'm simply doing that. But obviously, you know, I want to be able to do it, so I'm adding I'm mutating the STS string. So to do that, I'm going to actually define this as mutable here, and then I'm going to use this push _ str function to append the literal to a string, which now means when I can just print it with a reference to STS. So I've defined STS as a string, and it has the word hello in it. So STS has ownership of that, and then I'm going to use this push function, you can see, or method I think would be a more accurate thing, to push it onto STS. And you can see, yeah, I've got the same results, but I've just done it two different ways. One way was to append it as I'm printing it. The other way is to append it on using this push _ str method. Now, so let's consider this within a block and the scope. When any variable goes out of scope, Rust calls a special function for us called drop, which returns the memory our variable was using back to the allocator, and that's true in the previous example. So that's actually what's going on. Is this is where the memory is cleaned up in Rust. But in this example, I'm doing it with this particular type of string type. And again, as before, STB isn't going to be valid in the block until you define it. You can then use it, and then when the block finishes and the scope is over, Rust drops the STB variable, and it's no longer valid. I'm not going to do it, but if I was to reference this, it would be the same as the previous one, where I would get an error again. But part of this is, obviously we've already seen the scope, but I just wanted to show you within this, as they do in the example, they sort of introduce additional the additional string type. And this is important because of the way copying works on certain data types. When you're copying things from like one variable to another. So let's think about some variable interactions. So first of all, integers. So we've got x equals 5, y equals x. So again, we've done that. And if we look here, you can see, yep, it's quite happy doing that. And data types that have a known size at compile time, like integers, can be copied. Section 4.1 includes a list of all those data types. So what about string types? So we're going to uncomment some code here, and we're going to see actually what happens. So again, I could have probably done this here, but I wanted to sort of break it down into two parts here, just so you can see exactly where things go wrong. So let's deliberately, so we're going to define our string. I'm not going to do anything clever at this point with mutability. This is purely just to illustrate what happens when you attempt to copy a string from one thing to another with this string type. So one variable to another. So if we run this, okay. So actually, slight error here. Let me just redo that, because really that one I wanted to print out. I just didn't want to have two errors, because it's calling an error on one thing. Interesting. Oh, yeah, no, I did want to do it that way. Yeah, sorry, my mistake. Yeah, so let me take that back. That was deliberate. So we're getting a couple of errors here. Let me just walk through these yet. So we haven't used so ignore this for the moment. This is just help if this is intentional. So yeah, I know I'm not using S2. That's fine. What I want to illustrate is once we've copied S1 to S2, where might we run into problems? If we try and now reference S1, and you can see here it's not happy. So S1, the type string, you can't do a copy on it. It won't let you copy S1 to S2, and then if you subsequently try and reference the earlier version of S1, if you like, so you would kick up that error there. So in the case of the error caused, if you attempt to what's called deep copy a string variable automatically by just doing equals, you'll get an error. However, it's fine if you use this clone method. So in the case of an error caused, if you attempt to deep copy a string variable automatically, you can explicitly do this using the clone method to allow you to deep copy the string variable. And when you do that, you're good to go. Everything's fine. So that's the sort of, the compare and contrast between the two. Now, obviously, semantics for passing a value to a function are similar to those for variables, and I suggest you read through listing 4-3 in section 4.1 of the online Rust programming book, and work through and look through those examples in functions. And it's a similar thing to do with when you pass variables backwards and forwards through a function, how that affects things like ownership and scope. And there's annotations in there showing where the variables go in and out of scope, similar to what I've done here as well. And one last thing I wanted to try, because I'm curious again, as I'm doing this, I get curious about the sort of errors you're getting in here. So I'm going to just copy paste this piece of code. And it's not always wise to necessarily do this, like modify, copy and modify code. It's easy to make mistakes. I'm just seeing what sort of error I get now if I do this. So am I gonna, it should not create an error because I haven't used S2 in anything, but I should get still an error for S1 because I'm trying to print S1 after I've attempted this automatic copy just using equals. I mean, I'm using the word automatically here loosely to just imply that it's a sort of unthinking version of copy on the variable type of this string variable type. Yeah, there we go. That's probably a cleaner example. So you can see it's definitely not happy with me effectively making copies. And what's actually happening is, you probably gather here, instead of the copy, it's actually doing a move. So it's moving one to the other. It's moving S1 to S2. And because I've attempted to use S1, as far as it's concerned, that's, I've shifted ownership. I'm changing that stuff over. And as we said earlier, that's fine with certain types of variables. It's quite happy to let you do that in this example, like integers. But this second type of string variable, which you would want if you're doing a lot of changing of the variable, it'll just move it. And so if you then attempt to use the original copy, if you like, you then run into problems. But if you do want to maintain, you know, 2 instances of the variable, then you have to use that clone method there. Okay, so hopefully that makes sense. It makes more sense in combination with the, if you read through the section, you know, there's a lot of reading around ownership to really master it, but I thought it'd be nice to see again some examples where you can break Rust effectively, and the really helpful errors that you get back from that. So thanks once again for watching. Bye for now, and I'll see you in the next video.